Chapter 2, Descriptive Statistics. And the first section in the chapter is called Display Data. So the first definition is a stem and leaf plot, also called a stem plot. And what it is basically you're taking your data and you're separating it into where you can see the last data value. The best way, let me show you some steps how to do it, and then I'll just show you how to do it. So the steps to construct the first one, you have to arrange all the data in order. Then you separate the data according to the first digit, and then step 3 is you plot the data. And plotting the data is not what you would think by graphing it, it's putting it in the actual plot itself, the stem and leaf. Here's our first example. So an outpatient testing center, at an outpatient testing center, the number of cardiograms performed each day for 20 days is shown. Construct a stem and leaf plot for the data. So here are your data points, and I actually have them on the next slide as well, so I'll move to there. And what you're doing is you're trying to separate them into their digits, meaning that you have a stem and leaf plot, and what it looks like in a stem and leaf plot is it kind of looks like a T-chart. And on the left side are all the digits of the one's value, except for the last digit. The last digit goes on the right side, okay? So the stem is all the numbers up to the very last digit, and the last digit is called the leaf on the leaf side. So for instance, we go and look at these values, and you can see that all of these values are only 2 digits long. So that means the first digit, like 25, okay, the first digit on 2, the 2 would be on this side, and the 5 will be over on this side. So what you need to first do is put them in order, right? So you can arrange all the data in order if you'd like. So if we put them all in order, we would say 2 could be there. Then we move to 13 and 14, 20, 23, 25. I'm gonna have you pause it here, and you go ahead and do it, and then check your work when we come back. All right, so this is what you should get. And all I did was just list them from smallest to largest. And the reason for that is now I can group them. And you can see what I'm going to group them in is that everything with the first digits. In this case, it's going to be the 1 digit. And right here is just the 0. So that's going to be our very first stem and leaf. So we say 0. And then we have 2. Next we have 13 and 14. So we have the 1, we have 13, and we have 14. Then we have the 20s, which is, so there's our 20. So 0 is 20, 3 for the 23, and 5 for the 25. Next we have our 30s. So 30s, the 3 for the 30s. We have 31, 32, and we do have 32 3 times, so we do write the 2 3 times. Just because it's repeated doesn't mean we just write it once. We write it the whole time, as many times as it shows up. So I have 32, 32, 32, and 36. Next I have the 40s. I'll put the 4 there for the 40s. I have 43, 44, 44, and 45. And then last I have the 50s. So 5 for the 50s, and I have 51, 52, and 57. All right, this would be your stem plot, your stem and leaf plot right here. That's it right there. Okay, and really this is more for when you have smaller pieces of data. All right, you don't have 100 data values, only because this could go on and on and on, repetition. But the main thing is to see, for the stem and leaf plot, is to see where do the numbers really lie. So where the majority of our numbers lie, we would say maybe in the 30s. All right, so when we're looking at the number of cardiograms performed in the last 18 days, we would say about 30 per day. Okay. All right, next I want to talk about a line graph. And you can see the line graph. We're not going to work on it. I'm just going to show you. The line graph, you can see that it has the frequency as the y-axis, and on the x-axis, it's talking about what it's describing. So this comes from the text. It says the number of times a teenager is reminded, I believe it's to do the chores or something like that. And then you have the frequency. So they're not reminded at all. There's 2 of them. They're reminded 1 step looks like 5, and so forth. And you can see that the values, the frequency values, are all here, and then they're connected by lines, hence the word line graph. Now, we also have something called a bar graph. And again, not going to show you in full detail what a bar graph looks like. I mean, how to solve it or create one. We're going to get to something a little bit different, which is similar, but it is different. And a bar graph, again, just has bars, right? But notice the one thing, the next graph doesn't have this. There's separation between the bars. There's nothing in between here. There's a big gap. That's the difference of a bar graph and what we're going to do here shortly. But before we get into how to construct what we're going to do, and in our case, it is going to be a histogram. Before we start constructing a histogram, there's some background that I want to give you. So the first, so the data are in the original form, they're called raw data, and the frequency distribution is the organization of raw data in table form using classes and frequencies, and this is really what we're going to build upon right here. And then each raw data is placed into a category called a class, and the frequency of the class is the number of data values contained in a specific class. Okay, so their frequency is what on the last two graphs you saw. So here's kind of what a frequency distribution table looks like. So you have class limits, and some don't include this tally mark of it. This is just a very elementary way of making sure you count all the values there, and the frequency is really what you're looking at. So these two things are really what you can use to graph your histograms. So some more definitions before we get going here. The first one is the categorical frequency distribution. It's more like when you can put things into categories. So like I have, for instance, political affiliation, religious affiliation, major field of study, right? Then you also have something called group frequency distribution. There's a range of data that's large, and this is really what we work with a lot, is the group frequency distribution. So we'll say there's a range of values. So numbers like 10 and 15, and then 16 and 15, 16 and 20, and so forth. All right, so this is what we look at more. So I know I showed you class limits, but now we also have something called class boundaries. And you have, I've already labeled them for you. The class limits, we have what we call a lower class limit, which would be your bottom number here. And you have your upper class limit, which would be your upper number. Then you have the class boundary, and you can see the class limits are actual whole numbers here in our case. The class limits are the type of numbers that we have in our data. So if we were to have all whole numbers, this would represent our class limits, our data. The class boundary, you can see that it goes a little below and a little above. That's because we always go one more decimal place to it. And the reason for that is if I have a piece of data that says 35, well, instead of putting 35 here, you don't really know exactly where it lies sometimes, right? Now you also have something called the class width. It means how big is this class boundary? In our case, we subtract the 2 and we get 9. All right, we've already went over this here. All right, so how to construct a group frequency distribution. So there's 3 steps. Even though the first step I feel like has all the work. So the first is you have to determine the classes. So how you find that, or how you determine that? You find the highest and lowest values, find the range, and then select the number of classes desired. One thing is if it's not, the number is given. If it's not, then the rule of thumb is that you take the square root of the number of pieces of data. So if there was 100 pieces of data, you take the square root of it, it would be 10. So you would divide it by 10 classes. If, let's say, it didn't end up being nice, and it was something like, let's say you had 50 pieces of data. Well, when you take the square root of 50, you get 7.07. So you round to the nearest whole number, and you would say, okay, well, I'm going to do 7 classes. So next is then you find the width by dividing the range by the number of classes and rounding up. All right, and I'll show you here how to do that. And then select the starting points. You have to know how to get the lower limits, and then you find the upper class limits, and then you find the boundaries. That's all before you even now start to build your table. Now this is helping you build this table over here. It's helping you get all of these values. Once you get these values, then your next step is to tally the data. And once you have the tallies, then you can write the numerical frequencies. Now this step is not required. This is just an easy way to keep track of everything you are doing. Okay, really step 1 and 3 are the requirements here. Here's our first example. So it says these data represent the record high temperatures in degrees Fahrenheit for each of the 50 states. Construct a group frequency distribution for the data using 7 classes. So here's all of our pieces of data. All right, and you might have to go and go back to this. You want to take a screenshot of this or write it down. But I'm going to start breaking some of this data down. So the first thing is determine the classes. So the first step is we need to find the highest value. And in our case, our highest value here was 134, which was right here. So there's our highest value right there. Okay, now we need to find our lowest value. Our lowest value is 100, which shows up right here. All right, so there's our highest and our lowest. Next, we find our range. And to find the range, you take the highest value and you subtract the lowest value. So in our case, it's 134 minus 100. So our range is 34. And here in the example, I said I want 7 classes here. So there's 7 classes you're going to be using. So we're going to say that there's 7 classes. We're just going to state it so we remember. And then now we find the width of the classes. And how we do that is we say the range divided by the number of classes. So if our range is 34, and the number of classes is 7, this gives us 4.9. And when we find the width, we always want to round up. Even if it was 4.1, if it was 4.3, we would still round up to 5. So our width is going to be 5. And the reason for that is so that all of our data fit into the number of classes that we are trying to find. So next we have to find a starting point. So our starting point, the first is we start with 100, right? Because that's our lowest value. It's a nice value. And then our width is 5. So to find our next one, we have 105. So our first starting point is 100. The next one is 105. On the next one, we would add 5 again, and we say 110. And then we would just keep going to find all of our starting points. Also call our lower class limits. Next, we find our upper class limits. Where those come from, it's 1 less than here, 1 less than here. All right, so our first upper class limit will be 104. Our next upper class limit will be 1 less than here, which would be 109. And then we would keep going based on the values that we have. Now our boundaries are where the numbers lie. Okay, so our boundaries are always 1 decimal place further than our original data. And all of our data here, if you look at all of it, it was all whole numbers, which is going to 1 decimal place. If one piece of data had any decimal at all, we'd have to go 1 lower than that 1 piece of data for everything. In our case, it's all whole numbers. So we go from 99.5 because that is 1 decimal place lower than 100. And then our upper class limit is 104, so we go 1 above it, which is going to be 104.5. Then our next boundary would start at the upper boundary of 104.5, and it would go to 109.5. You can see our width now is 5 between our boundaries, right? Our width is supposed to be 5, and between here is 5. Then, of course, we would keep going. So let me get to what our table looks like. So here's what we have. We have class limits, class boundaries. We're in the tally market, and then we're going to do a frequency. This is our group frequency distribution table. So first is our class limits. And we first said we would start with 100. We go to 104. The next we said 105 to 109, and then we said 110 to 114. Or we can keep going. So that's what I'm gonna have you do. I'm gonna pause this, I'm gonna have you pause this, and then when we come back, you have the answer. Go and pause now. Here are the values that you should have gotten. Now that we have the class limits, let's go to class boundaries. We started with 99.5, and we went to 104.5. The next one we said was 104.5 to 109.5, and then we would keep that trend. So I'm gonna go ahead and pause it, you pause it, and finish the rest, and then check your work. Okay, so go ahead and check your work here, and you should have those same class boundaries. So once we have the class boundaries, then we start looking at our data and say, okay, well now I need a tally. What I mean by tally is just to count the values that lie inside those boundaries. So here we go. So here's our data again. We're gonna look and we're gonna start saying, what numbers lie between 99.5 to 104.5? So since they're all whole numbers, the numbers that we're looking for are 100, 101, 102, 103, 104. Those are the numbers we're looking for in all this data. So we start going, let's say, okay, well, 100 is 1. As we start scanning, right, we're scanning, nothing there. Then we're scanning through here, nothing there, still nothing, still scanning. You keep going, I'm gonna go a little faster. And then bingo, there's one right there, 104. So 104, there's another tally. And we'll keep going, nothing there, nothing here, nothing between that. All right, so the tallies that we have between the class boundaries of 99.5 to 104.5 is only 2 values. And you would do that for all of the class boundaries and or class limits. So I'm gonna go ahead and pause this, and then you go ahead and do this, and then come back. All right, so you should get this. Your tally marks look like this. And in order to check them too, if you recall, we had 50 pieces of data for temperatures from the 50 states. So you should, these tallies should add to 50. Well, instead of counting tallies, you can always just go to the frequency part. And the frequency is just you writing the numbers of tallies. So the first one, there's 2, so you just write 2. Next one is 8, you would write 8. So we keep going, you would get these values, 2, 8, 18, 13, 7, 1, and 1. So why all this? Because we need the group frequency distribution table to now create our histogram. This is a stepping process. So now a histogram. A histogram is a graph that displays the data by using touching vertical bars. And here's the key, that they are touching vertical bars. All right, unless the class is 0, then there's no bar for it to touch because that's the bottom. And that represents the frequencies of the classes. So here are your 3 steps. Draw and label the X and Y axes. On the X axis, I should have little dashes in here. On the X axis, label the class boundaries of the frequency distribution. And then step 3, plot the frequencies for each class and draw the vertical bars. And so we are going to use the exact same problem. We're not going to recreate it all. Same problem, didn't change anything. We've already created this table, right? This group frequency distribution table. But what are we really graphing here? So in a histogram, we have 2 pieces of things that we need to put on there. So we have our class boundaries, which is going to be, if you want to call it the x-axis, and then we have our frequency, which is what you would call the y-axis. So these 2 are what we are going to be graphing. All right, you can see here's what we have right there. This is what we're going to use to construct our histogram. All right, so let's construct this. All right, so first thing, we first have to look back and say, okay, what's our highest frequency? Our highest frequency is 18. So you have options. You can go up here and put 18 dashes if you want, or you can go by 2s. And going by 2s is what I'm going to go by, so I have to make 9 little dashes. So I'm going to go by twos. So I'm going to go 2, 4, 6, 8, 10, 12, 14, 16, 18. Again, this is our frequencies, but we're talking about the states. So this is going to be number of states. Either label our X and Y axes as I put the steps. All right, next are our class boundaries. So if you remember, here they are right here. Right, here's all of our class boundaries. So these intervals are what's going to go on the x-axis. So I'm going to bring it off the middle here. So there's 1, 2, 3, 4, 5, 6, 7. So our smallest one right here at 99.5, that's going to go right here, 99.5. The next one, which is 104.5, that's going to go right here, 104.5. And what you really are doing is you're putting all of these lower class boundaries, 99.5, 104.5, and you're writing all of these all the way across. And so you'll also have to add this one at the end. All right. So we have next up, so at 104.5, we have 109.5. 109.5. We have 114.5. We have 119.5. 124.5. 129.5. And then our last one is 134.5. So we know that our frequency was the number of states, but what is our data representing? And the data represents the record high temperatures in degrees. So this is temperature in degrees. So we could say Fahrenheit. So if we go back to our steps, first step was draw and label the X and Y axes. Done. On the X axis, label the class boundaries of the frequency on the frequency distribution. Done. And the last one is plot the frequencies for each class and draw the vertical bars. That's what our next step is. So we have our first group. And our first group of 99.5 to 104.5 right here was 2. So we're going to go up to 2, our vertical bar. Do our best here. And we're also going to write the value right above it. It's not required. Texts don't require it. This is not something that you're going to see everywhere, but this is what I would like you to do in order for you to really make sure that our data is as organized as possible. Now, between 104 and 109, if you go back to our data, here was 8. So we're going to go up to 8. And notice how it's like a bar graph, but again, our lines, our vertical bars touch. We're going to write the number above 8. And this is only for more accuracy, that's why we write the number above it. Next was 18. So 18. Next one is 13. Then between 119 and 124.5, we have 7. And then we have 1. And then our last one is also 1. All right, so this would be our histogram fully completed. All right, next section, chapter 2, section 2, measures of the location of the data. And this one, we can divide our group of data into 4 equal groups. All right, we call them quartiles. And the main one that we talked about, we denoted by quartile 1, quartile 2, quartile 3. And then the last quartile would the rest of the data lie in. So these are ones we really find. And also quartile 2 is the median. That's also what we call the median. How do you do this? First, you arrange the data from lowest to highest. Step 2, you find the median of the data values. Step 3, all right, find the median of the data value that falls below quartile 2, which is your quartile 1. And then step 4 is find the median of the value that lie above quartile 2, which is quartile 3. So first, let's learn how to find the median. The median is the midpoint of the data array, and the symbol for the median is MD, used frequently. So steps to find the median. First, you have to arrange the data values in ascending order, which was the exact same thing we did here, so you already have to do it anyway. And then you determine the number of values in the data set. So are there an even amount or an odd amount? If there's an odd amount, then the middle data value is the median. If there's an even amount, then you find the average or the mean of the 2 middle values. And in order to do that, you add them together and divide by 2 to find the average. There's only 2 values there. So let's practice it. So what happens when you have an even? This actually should say odd. My fault. This should say odd. All right, so I have 1, 2, 3, 4, 5 pieces of data. All right, so that's step 1. So I've ordered them from smallest to largest right here. Then I have 5, which is odd. And then now I take the middle. And for us, it's right here. Here is the middle piece of data. How do I know that? Well, look, I can always do n by n. So I have my fingers, but you can't see it. So I'd say I would cross off as I go. 1 and 1. 1 and 1. There's my middle piece of data. That's the easiest way of doing it, elementary way of doing it. So you would say that that piece right there, this is my median. All right. Okay, now what happens if we have it even? So you can see again that we have 8 pieces of data. Right? So put them in order. So there they are in order. There's 8. It's an even number. And then so what I do is I say, okay, well, what's my 2 middle pieces of data? We can cross off like we did before. Cross off 1 and 1, 1 and 1, 1 and 1. And we're left with these 2 pieces. So those 2 middle pieces, what you need to do next is find the average of them. In between here is where the median lies. That's how to find the median. We say 764 plus 856 divided by 2 to find the average. This gives you 810. This is your median of this data set. All right, the next thing we need to find is what we call the IQR, which is abbreviated IQR, but it is our interquartile range. And our interquartile range is found by taking the 3rd quartile and subtracting the 1st quartile from the 3rd quartile. So here's an example of what we need to do. So step 1. Remember, step 1 was to order everything. All right, for finding quartile 1, 2, and 3, we need to order everything from smallest to largest. So here's us doing step 1. So smallest value is 9. Then we have 12, 15, 16, 18, 19, 20, 22, 24, and 25. So there's all of our small pieces. They're all of our data from smallest to largest. Next, we find the median, or the second quartile, and that's, again, what we just did. We count how many we have, and then we find if it's even or odd, and make our decision. In this case, there's 10, so we know it's even. So we're looking at the two middle pieces, the pieces of data, which are right here. And so in order to find the median, or the quartile 2, we're going to say this is our quartile 2, and that equals 18 plus 19 divided by 2, which is 18.5. This is our quartile 2. So step 3 is find the middle of the lower half of the data. In order to find a lower half of the data, it is right here between. There's the middle of the data. So the lower half is over here. So what's the middle piece there? Well, this is odd. Right? There's an odd number. There's 5. So that means I have this right here. This value right there is a quartile 1. That was the middle piece of that lower half of data. Now I need to come over here and look at my upper data, which is 5 there. So that means the middle, which is right here, this is my third quartile. So now I found my first quartile, my second quartile, and my third quartile. Last thing it says, find the IQR. The IQR is third quartile minus the first quartile. In this case, it's 22 minus 15, which is 7. So here are all my pieces: 15, my 18.5, and then my 22. The four pieces of data that I need to find. Next, we need to find what we call an outlier. An outlier is an extremely high piece of data or a low piece of data compared to everything else that you have. Now, sometimes you can look at it like, oh yeah, that's definitely way out there. There's no need to show. And sometimes there isn't. All right, if our data, a lot of it was between like 1 and 5, and all of a sudden you had a number like 100, then 100 would probably most certainly be an outlier. But there's a mathematical way of finding what an outlier is, or identifying where the outlier is, I should say. So first step, arrange the data in order from lowest to highest, which most of the time we're doing anyway, and find quartile 1 and 3. Then you find the IQR. So basically our last example. Once you find the IQR, then you multiply it by 1.5. Then you take that number, whatever it is, and subtract it from quartile 1. And then you also add it to quartile 3. So now you have 2 data, and the number, 2 numbers, and those numbers we're trying to see is, are there any numbers that lie outside of those values? And it's probably easier for me just to show you. So here's our next example. So check the following data set for outliers. Well, I've already numbered them all in order, so you don't have to worry about that. It's an even piece of data. So we know that this is the middle here. We do not need to find the median or the second quartile to find an outlier. So we're going to skip that part, and we're going to go straight to finding quartile 1 and 3. So quartile 1, here's the middle here. So we would say 6 plus 12 over 2, which is 18 over 2. So our quartile 1 is 9. And then upper half of data, here's the middle here. So we would say 18 plus 22 over 2, and this gives us 20. Right, so quartile 3 is 20. So next we need to find the IQR. The IQR is quartile 3 minus quartile 1, so it's 20 minus 9, which is 11. This is all step 2. Now step 3 says I'm going to take and multiply this value. So I'm going to take 11, I'm going to multiply by 1.5. This gives us 16.5. We're going to take this value and we're going to subtract it from quartile 1, and we're going to add it to quartile 3. So if I say 9 minus 16.5, well, that clearly gives us a negative value, right? And we don't have any negative values, but just so we can write it, we say this is negative 7.5. This would be our lower numbers that we're looking for. Now the upper ones, we would say 20, right? That was our quartile 3, and we're going to add 16.5. So that means that you're looking for a number above 36.5, 36.5. So now we're going to try to identify the outliers. So this is step 5. Step 5 says what we're going to do is say, is there anything below my lower value here? And is there any number above this value here? So below -7.5, which would mean that we need a negative value. We have no negative values. So nothing there. So no outlier. That's on the lower end. Now we look at this number. Are there any values above 36.5? And that answer is yes, 50. So we would say that 50 is a possible outlier. Now, why do we say possible outlier? More than likely it is an outlier if the data is given to you like this, but we always say possible due to the fact that we could have written the data down wrong. We could have an error in the data collection. So it's possible that it's not even an outlier. It's possible it's not even an actual value. So maybe we wrote 50 instead of 5. All right, so we're going to shift gears. Definition here, we're going to find the mean. We already talked about this, the average of the sum, right? So you're going to start the average. So we're going to take the sum of the values and divide them by how many values you have. We have something called the sample mean, and we have right here, it's called X bar. And it's calculated by using the sample data. And then all you're really doing is just a fancy way of saying, we're going to add all the data together and then divide by how many we have. Okay, this is what this means. This means summation. And then your n, you can see right here, n represents the total number of values in the sample. Right, just find the average is all it is. Just putting it more mathematical. There's something called the population mean, and it's denoted by a different variable right here, and that's pronounced mu. And it's calculated exactly the same way, except for now we use a capital N that represents the total number of values in the population. So notice there's a difference. One sample, one population. A population is everything, and a sample is a piece of that population. Most everything we work with is sample. Population is not always applicable because you have to have everything or everyone involved. A sample, you miss one thing or one person of the population, boom, you have a sample. So here is our first example here. The data show the system-wide sales in millions for U.S. franchises of a well-known donut store for a 5-year period. Find the mean. Okay, so it shows the system-wide sales for U.S. franchises of well-known donut store for a 5-year period. So we are taking a sample of all of the donut stores. So we know we're going to be using sample. In our case, it's X bar. So what we're doing is we're adding all of the X values and divided by N. So we're taking 221, 239, 262, 281, 318, and dividing by, we have 5 of them. 1321 over 5, sorry. That gives us 264.2. Now we're not going to say it's $264.2. Right? It's in millions. So we're going to say the mean amount of sales for the stores over the 5-year period is $264.2 million. I'll repeat that. The mean amount of sales for the stores over the 5-year period is $264.2 million. That's how you would answer this question. Next, we're going to talk about the mode, and that's in this section. So the mode is a data set that is most repeated, and we have 3 different ways the data set can have. We have unimodal, where there's only one number that's mostly repeated. We have bimodal, bi means 2 values are mostly repeated. Or we have what we call multimodal. We don't go into trimodal or quadruple modal. We go into single, double, or more than 2. Now, next, let's talk about skewness. So if we look at a graph, and here's a histogram, and it says in a symmetrical histogram or graph, it's perfectly symmetrical, which means the mean and the median are the same. Here's your highlights here. The mean and the median are the same. We have two more that we're going to look at. We're going to look at what we call skew left. The data is pulled up to the left. You can see to the left, it comes out a little, it starts tailing to the left. This is called skewed left. And here, the mean is less than the median. And they are both less than the mode. The last one is skewed right. The data is pulled out to the right. As you can see, it's got a tail out here, starting to tail from out here. And here, the mean is the largest, and the mode is the smallest. So that's how you can, that's the conclusions you draw from a skewed right graph. That section was a lot shorter than the last bit, so we're going to move to the next section. That's the measures of the spread of the data. So what are we talking about? We're talking about standard deviation. This comes right from the text. I wanted to pull it right from the text. It says provides a numerical measure of the overall amount of variation in the data set, and it can be used to determine whether a particular data value is close to or far from the mean. So it's really talking about the spread of the data. So is the data really close together, or is it really spread out? All right, if it's closer together, then your variance is smaller, which means your standard deviation value is smaller. If all the data is really spread out, right? So you have numbers from like 1 to 100. Let's just, for instance, then what happens is your variance will be large and your standard deviation will be larger. Okay, if you have numbers, if you have let's say 20 numbers that are in between 10 and 15, well then your variance and standard deviation, there's a lot of values in between 10 and 15, so it's going to be very small. So if I have 20 numbers between 1 and 100, well that means they could be spread all the way out there. So then my variation would be much larger and my standard deviation would be much larger than the previous example. So here's how you find it. The population variance, we still need a population and a sample variance. So the population variance is you use sigma, so sigma squared. And then this is just saying that you have, again, this is the sum of the x value, so it's the data values minus mu, right, which is our average. And we square it, and we divide by n, which is the population size. Now we also have something that we can write down, and it's very similar to this. It's sigma squared equal to the sum of, and we would say the frequencies of x minus mu squared all over n. And the reason why we say f for frequency is because what if that piece of data shows up more than once? So we're going to multiply it instead of just counting over and over and over again. You can write it multiple times in the table. You're going to see if you want to, or you can just you can put f for frequency in there. So what is the population standard deviation? All it is the square root of the variance. So once you find the variance, then you take the square root, and then boom, you have the standard deviation. So again, this is population standard deviation. We'll mostly work with sample variance or sample standard deviation. So there are samples. So the main difference is that you have an S for the sample, and then we have X bar, which is the mean of our sample. This should be sample mean. Sorry, I have a typo here. This should say sample mean. This should say sample size. The same thing, I could say S squared is the sum of the frequency of X minus X bar squared all over n minus 1. And the reason why it's n minus 1 is because mathematically it talks about the error that we could have. So we try not to say all of it because we don't know it all. So it's the best estimation when we have large quantities inside of our data set. All right, so population standard deviation, again, it's the square root of your variance. So here's the way you compare them. So you can see that here is our population, and then here is our sample. All right, and the main things that change, instead of mu, we have S, right? That's it. And then instead of sigma, we have S, and then we have mu instead of X bar over here. And then the last one is that for the population, we take n, which is the whole population. So if we have a sample, then we take how many we have minus 1, and we divide by that value. All right, here's our last example of this chapter. So what we first need to do is come up with a table. That's how we do this. So first off, let's read this. So find the variance and standard deviation for the data set for a brand of paint. The number of months the brand lasted before fading was 10, 60, 50, 30, 40, 20. Because we don't know if this is a full population, we can't assume it. So we're going to assume that this is a sample. Right? If it says population, then you know population. If it doesn't, we assume sample. So how we start our table is we start with X. And what we have is, in fact, I'm going to write a little smaller here. I'm going to have a lot here. So we have X. The next part is going to be F times X. Our next column is going to be X minus mu. Oh, sorry, not X minus mu. We're talking about sample, so it's X bar. And then our last one is going to be X minus X bar squared. Well, we have 6 pieces of data. We have 10, 60, 50, 30, 40, and 20. All right, so remember F is our frequency. So how many times does 10 show up? Only once. So 10. 1 times 10, which is 10. And then frequency for 60, it shows up once, times 60 is 60. Again, you don't have to do the F times X column. I only put in there in case you have that value more than once. It saves you some time when you have a bunch of data values that could be repeated. When they're all not repeated, this column is not necessarily needed. So we have 1 times 50, which is 50. We have 130. We have 140. And we have 120, which is 20. Next, what we're going to do is we're going to take and we're going to find the average. So we're going to add all of these values up and then divide by the total number we have. So we're going to use X bar. So our X bar equals the sum of the frequency times X divided by N. So if we add all of these together, the 10 plus 60, again, what I'm adding up is 10 plus 60, 50, 30, 40, and 20. If I add all these together, we get 210 divided by 6, which is 35. So 35 is our mean, it's our average. So now what we're going to take is we're going to say, now we're going to take X in this next column, X in this case, which is 10. Now we're going to subtract the mean, which is 35. Let me try to give myself some more space here. So 10 minus 35, which is negative 25. And then we'll keep that pattern going. So this one is 60 minus 35 equal to, and we do those, that's positive 25. I'm going to ask you to go ahead and stop this, and I want you to try to finish that column and then come back and it'll be done. So we're going to take a look, see if you got those same values. And again, it's okay to have negative values and positive values because the goal is, if you were to add all these values up, you should get 0. All right, you have to get 0. Not you should, you must. And so I put an error in there, as that way you can see that I did mess up somewhere. So let's say you keep going, oh yeah, I did my math right, and I keep going. But let's go ahead and calculate this. If I have negative 25 and 25 right here, this gives me 0. 15 minus 5 is 10. Plus 5 is 15. And minus 5 is 10. But those should be equal to 0. So, okay, I've done something wrong. Go back and check my math. This one's good. Good. Fine. 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 And my error right here is right there. This value should be negative 15. So then we can go back and check it again if we like. This gives you 0. That gives you 0. and then this gives you 0. So all of my variations there should be 0. Next, I take and I square these values. I'm going to take these values, I'm going to square them, and then they go here. So the first one is 25 squared, which is 625. All these values should be positive. So these are not the values that should be adding to 0. They're all positive. You can't add a bunch of positive numbers to 0. 25 squared is 625. 15 squared is 225. 25, right? Negative 5 squared is 25. 5 squared is 25. And negative 15 squared is 225. So next, you're going to add these up. And so this is going to give you your variance. Your variance, again, is summation of x minus x bar squared all over n minus 1. And if I add all of these values, I'm adding all of these up right here. This gives me 1750. So 1,750 over my n, which is 6 minus 1. So my variance, my s squared, is 350. It's a very large variance, which means what? That my data is spread out. It's not super close. So here's your variance. That's what it says to find the variance and the standard deviation. Well, in order to find the standard deviation is just that value squared. So S equals the square root of 350, which is, sorry, it should be approximately is 18.7. So here is my standard deviation. And all that is saying, again, is that my values are very spread out. If the values are near the mean, the variance will be small, right? If the values are not close to the mean, then my variance is very large. Again, my variance is very large. My standard deviation is pretty large. What are small variances? Numbers like 0 to 10, that's a pretty small variance. Okay, which means when we take the square root of them, then now I'm getting closer to like 0 to 3 on my standard deviation. All right, you can look at our data. Look, we start at 10, and we go all the way to 60. It's only 6 pieces of data, but we're all in 10 increments away. So the data is pretty spread out for only having 6 values.